Okay.
I'm checking the reflection. Yeah. Just a laugh.
Oh, and did you receive by any chance the chapter 12 to 14 homework of group 9, Professor?
Homework, probably so, because I checked the homework before.
Okay, thank you, Professor.
I would check, but if you you can send it again, to be on the safe side.
Okay, Professor.
And let me know, like, you send it again. I'd ask you to send it again. Okay.
I just sent it last night.
Oh, I haven't checked yet.
Okay, Professor.
Professor,
Uh-huh.
it's wrong, group 8.
What group are you in?
Group 8.
Group
8.
Oh, group 8. And the name?
Terrell DeLong.
Sherelle? Okay, I got you.
And then also Anne from group 8 is here too, with having audio.
When they get together, they can let me know.
Okay.
Okay.
Hi, Professor.
Uh-huh.
Reja Teodoro from Group 10.
Teodoro from Group 10. I got you.
Okay, thank you.
Oscar Anguiano from Group 5.
Group 5. Oscar, got you, Oscar.
Hi, Professor. Adriana Velasco from Group 4.
Group 4. Velasco, I got you.
Thank you.
Professor?
Ashley
Gutierrez, Group 4, is here.
Group 4. Got you.
Thank you.
Professor?
Uh-huh.
This is Kimberly from Group 10.
Kimberly, I got you. Anybody else? Okay, group 1. I'm missing only one person missing from group 1. Group 2, I'm missing 1, 2. Group 3, I'm missing.
Hi, Devin's here, Group 5.
Devin, Group 5. Let me see. Devin. Yes, I got you, Devin. All right. Everybody in Group 5 are accounted for. Group 5, everybody present. Group 4, 1, 2, 3, 4, 5, 6. One person missing from Group 4. Group 3, 1, 2, 3, 4, 5, 6. One person missing from Group 3. Group 2, 1, 2 people missing from Group 2. Group 1 person missing from Group 1. Group 6, 1 person missing from Group 6. Group 7, 1, 2, 3 people missing from Group 7.
Courtney from Group 7 is here.
Courtney?
Yes.
I got you, Courtney.
Thank you.
All right. And Group 8. 1, 2 people missing from Group 8. Group 9. One person missing from group 9. Group 10. Group 10, all are accountable. All right, we're going to start the class. Okay, so today we didn't celebrate because this is our last chapter for discussion. Everybody should celebrate, celebrate, celebrate. All right, so chapter 14.
Hey now.
Amen. Acids and bases. Hallelujah. All right, so acids and bases, we're still talking about the definition of chemistry. Don't forget that. Last day, chemistry is a study of what? Can somebody tell me what the definition for chemistry?
The study of matter.
And
Energy?
and composition of matter, right? So we've been studying chemistry concerned about matter and its composition, and so everything related to matter is quite interesting. All these things. So now we see matter can be acid, can be bases. So we're going to find out today. All right, what's different between those two? Now, so here here's the definition for acid. An acid is any substance that releases hydrogen ions, H plus, into water. Anything that dumps H plus into water, that's an acid. What's that H plus for? That means hydrogen has one electron, it gives that one electron away. So all it has now is proton and no electron. So that's one of the reasons why hydrogen ion is referred to as a proton. When you hear people say proton, they mean hydrogen ion. Litmus paper turns red in the presence of hydrogen ions. Litmus paper would turn red when hydrogen ions are there. They'll turn blue.
Professor?
You know.
My name is Claudia. I'm from group 8.
Claudia, group 8.
Group 6, sorry.
Yeah, you got me there. I said, whoa. Group 6, yeah, that's right. I couldn't find you in group 8. I said, all right. So acids have a sour taste. So when you eat lemon, that should flag you down that you have acid present in there. When limes, vinegar is acid base because it tastes sour. So anything that you eat that is sour, you know it has some acid, hydrogen ion in it. A base, how about base? A base is substance that releases hydroxide ion. Anytime you see something releasing hydroxide ion, which is a polyatomic ion, OH negative, into water, you know that's a base right there. Litmus paper turn blue in the presence of hydroxide ion. So if you have litmus paper, that's one way you can test something. Is this acid or is this base? Red litmus is used to test for bases. Bases have a slippery, soapy feel. It's slippery like okra. Okra is slippery. Eh? Yeah, bases also have a bitter taste. The taste is bitter. You know, I take fig leaf and make tea out of fig leaf, and it's bitter. So you know it has a base in there. And I take guava leaf, any kind of stuff you drink that's bitter, you know it has a base in there. Milk of magnesia is used as a base. You guys are familiar with that one. All right. So here's a table here, table 14.1. He has some properties. Tables are so good, as I mentioned, from time to time. You always go on a table, you can pick something from a table or from graph. So scientists always engage in developing tables and graphs and charts. Taste, so acidic solution, that's sour. Base is bitter. Feeling, acidic solution, there's no feeling there. And basic, this feeling is slippery and soapy. Litmus paper will turn red in the presence of acid. It will turn blue in the presence of a base. pH. The pH is scaled from, let's say, from 0 to 14. All right, and 7 is neutral pH. 7 is not a base, it's not an acid. So pH 7 is neutral. Greater than 7 is so less than 7 is acid. So 7 is in the center, 1 through 14. So from 1, as you start going towards 7, you're going toward less acid. From 7 going up to 14, you're going toward higher base. Neutralization, you did a reaction, God did that neutralization reaction. React with bases to give it salt. When an acid react with base, the result is salt and water. We've done a lot of that, even in problem solving. React with acids to give it salt and water. All right, recall. Pay attention to that one. Every time you come across the word recall, that means we've done something about it. Recall that an acid and a base react with each other in a neutralization reaction. We talk about different types of reactions, and neutralization was one of those that we talk about. So whenever there's a neutralization reaction, you have the acid going. We'll take a look. I'll be right back. Hold tight.
Double replacement.
Okay. So when an acid and a base react, water and salt are the result. Keep that in mind. But you got to pay attention to the fact that both of them must be the equal amount. If the acid is more than the base, then the acid react with the base. There's some of the acid that didn't react because you don't have enough base, it will still be there. Vice versa. For example, nitric acid reacts with sodium hydroxide. You got that with sodium hydroxide already. To produce sodium nitrate, that's the salt. Sodium nitrate is the salt and the water. So here's HNO3. Now, agua, all right, aqueous. And then you have the salt is NaNO3 as product and H2O as a water, liquid water. Any questions so far? A pH value expresses the acidity or basicity of the solution. So when you mix, we talk about solution already. A solution is defined to have a solvent and a solute, right? So everything here solution, in your mind, solvent and solute should be operating in your mind. Most solutions have a pH between 0 and 14. So when you make that solution up, you want to find out what is the pH of that solution that you made. All right? How many hydrogen ion present in there? Is there more hydrogen ion there or more hydroxide ion there? That's a good thing. That's what the pH is for. It tells you what you got. All right. Acidic solutions have a pH less than 7. All right. So you take a pH probe, like a guy was doing in the lab. As the solution becomes more acidic, the pH decreases. The pH gets smaller. All right. I mean, it's more acidic. I mean, you're going from 7 going toward 1, 0. Okay. This solution have a pH greater than 7. Going up, the higher up you go. Okay. As the solution becomes more basic, the pH will increase. All right. So these are things that these are basic things you want to know about solution. If you're in a solution making business, they are so good at it. Some people make solutions, they don't even worry about finding out what the pH of that solution is. Go to a pH meter and say, okay, I'm going to find out, is there any pH, where's the pH of this solution here? Or does they have any? Okay, so here is a chart right here. A solution can be classified according to its pH. All right? So let's take a look. Let's spend some time on this one. Strongly acidic solutions have a pH less than 2. Look at HCl. The M meaning molarity. The capital M is molarity. Stomach acid. So the acid in our stomach is HCl. Okay? So many people have a whole lot of that. So they have to keep taking becamoniza, blah, 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 take all that stuff there. They have, the environment is too acidic. Strongly acidic, strong acid, 1 and 0. Weakly acidic from 2 to 6. What do you find there? Lemon juice, vinegar, wine, grapes, orange juice, normal rain. I collected several years back. I collected rain and I bottled the rain. Correct. What you do is just take when it's raining, take a empty container and put it right in the middle of the ground, whatever it is, and don't let the rainwater touch anything else, but just fall right straight into the container. You collect that rain, maybe you can put it in bottle and put the year on it. All that is interesting. I have a couple of rain like that, except from years back. Milk, pH balance shampoo. If you use shampoo, so from this day forward, whenever you're using something, you start thinking about what is the pH of this thing. That means how many hydrogen ion present. So neutral pH, if you do anything and the pH is 7, then you know that is no acid in there and no base in there. Eggs, seawater that you're supposed to be collecting, ocean water, baking soda, and acid, make a magnesium soap. I make soap all the time. I make bar soap and I make liquid soap. It takes me 14 to 15 hours to make liquid soap. Household ammonia. I used to teach the liquid soap making. So if you're interested, let me know after this class. If you want to learn how to make soap, let me know. All right. Liquid bleach. Okay. Strongly basic, 13 and 14. Drain cleaner, sodium hydroxide. So this chart is interesting. And so you get to know what the pH of the solutions are. Buffer, that's another. Buffer is a solution. But a buffer just like a shock absorber on cars. If you're a lady and know something about cars, you know what shock absorber is. But the guys should know. Some guys probably don't even know what shock absorber is. But most guys will know what a shock absorber is. A solution that resists changes in pH when an acid or a base is added. Now, I always refer to mothers. Mothers are good shock absorbers. Mother can take anything from the kids. The kids can do anything. They try to ignore that. So mothers are a great buffer. A buffer is a solution of an aqueous weak acid and one of its salts. So to make a buffer solution, you got to have the weak acid and the salt of the weak acid. How do you get the salt? From the acid-base reaction. Now, when we talk about, you can make a neutral salt. Let's talk about the acid-base reaction. We have a strong acid reacting with a strong base. That is a neutral salt. Strong, neutral. All right, but we have a weak acid and a strong base. That is a basic salt. Keep track of that. If you have a strong acid and a weak base, that salt you just made is an acidic salt. You see the difference there? You make salt, acid-base reaction. You make salt, but is the salt neutral? Is it acidic or is it basic? Those are the things that you want to concern yourself with. All right, citric acid and the sodium citrate is a salt. Make a buffer solution. So now you see citric acid is a weak acid. Okay, sodium hydroxide is a strong base. So the citric acid will be a basic salt, make a buffer solution. So you have the weak acid, and the salt of that weak acid give you a buffer solution. That's how you make buffer. When the acid is added to the buffer now watch this, why it's called buffer. When the acid is added to the buffer, the citric reacts with the acid to neutralize it. So therefore, the change in the pH is not significant, not too big. Because what happened is the citric can't right away rushing to react with the hydrogen ion. You see? So therefore, the pH doesn't go too far. All right? So that's what a buffer is all about. When a base is added to the buffer, the citric acid reacts with the base to neutralize it. So therefore, when you have a buffer solution, and you can add base, you can add acid there, the pH change is not drastic. It's not drastic. That's what makes it a buffer solution. All right. A shock absorber. Okay. The change when you borrow money from mama and you don't pay it back, the change is not so significant. She's gonna forgive you. All right. That's what it is here. That's how I make mother a good buffer. They can, you can do all kind of stuff, and she just gonna forgive you and ignore you. And they're wonderful people. Yeah. All right. Savende Arrhenius proposed, if I would remember this guy here, definition for acid and the bases in 1884. That was a very good year. Arrhenius acid is a substance that ionizes in water to produce hydrogen ion. The acid you put in water, it from ions, hydrogen ion, and hydroxide ion. Its base is substance that ionizes in water to release hydroxide ion. So this is something that he came about in 1884 when people didn't even know about that stuff. And so he wrote something about it. For example, HCl, which is a strong acid, is this type of acid, and sodium hydroxide is this kind of base because HCl will release hydrogen ion in water, and the sodium hydroxide will release hydroxide ion. So any acid that releases hydrogen ion, any base that releases hydroxide ion will be the Arrhenius acid and base. All right. But that some other guys did some study. We're going to talk about them now. They found out that there are some bases that do not release hydroxide ion, but they are still bases. All right, and so forth. So we're going to find out. So acids have very varying strengths. All right, because of that pH we just talked about. The strength of an ionized acid is measured by the degree of ionization in solution. How does it ionize in solution? Ionization is a process by which molecules, we hear molecule, what type of bonding we're talking about? Covalent bonding, which is the intra type bonding of a polar compound ionized to form cations and anions. The acid HCl ionizes into H+, Cl- in solution. All right? So bases also have varying strengths. The strength of an ionized base is measured by the degree of dissociation in solution. Let's look at the term dissociation. It's a process whereby already existing ions of an ionic compound simply separate existing ion. You see, dissociate meaning ion come apart. The formula unit of NOH dissociate into sodium plus and OH minus. NOH. All right. Now, so strong acids ionize extensively to release hydrogen ions into solution. You know what a solution is? Solvent and solute. HCl is a strong acid, ionizes 100%. So here's the stuff you gotta remember. Table 14.2 is very, very important. And I always allow students to know this table here. There are some things that are not supposed to be there in terms of strong acid, but these are, they're just showing you that arrhenius acids. Okay, anything that say 100%, that is, there are 6 strong acids. You need to know them. And they have 8 strong bases. 6 strong acids, 3 of them are here. Now we need to research the other 3. Okay, hydrochloric acid is a strong acid, so it is 100%. Nitric acid, strong, 100%. Sulfuric acid, strong, 100%. Anything that is not on the list of the 6 strong acid, that will be considered weak. So we need to look them up before the class is over. I'll find out from you. And the bases too. There are 8 bases. All right. So all arrhenius acids have a hydrogen atom bonded to an acid molecule by a polar bond. We talk about polarity. In a covalent bond, the species that is more electronegative pulls the electron to itself, creating partial pole positive and partial negative. That's what we mean by polarity. This bond is broken when the acid ionizes. So the bond breaks, and now you have the polar water molecules help ionize the acid by pulling the water has finger. It can pull stuff into itself. The hydrogen atom away. So look at the HCl. All right. So the acid-base reaction, the acid is always donating hydrogen ion to the base, and the base will accept the hydrogen ion. Keep that in your mind. So HCl, which is an acid, is going to donate the hydrogen ion to the water, which is the base. Water can be a base, can be an acid. All right, it plays 2 roles. It plays a role of an acid, it plays a role of a base. Now, in the case of a strong acid, or if it's in the presence of a strong acid, it's not going to be acting like an acid. It could be acting like a base. So, the HCl will donate this hydrogen ion to the water, and then what happened? The water, do you know the water, way back when we started the structure of water, and we said the angle was 104, all right, and we said the shape was bent shape, you remember that? And the geometry was tetrahedra, remember that? Bent and tetrahedra, way back there, jogging your memory. All right. So therefore, water has 2 lone pairs on the oxygen. You don't see it there now, but we talk about it. So the hydrogen ion, which is electron deficient, has a positive charge, no electron. It's looking for electron for bonding. It takes two electrons or pair electron to form a bond. And remember I talk about coordination. In a coordinating covalent bonding, one species provide all of the electron. We went past that. We even showed that in ozone. Okay, and so the hydrogen ion will be bonded to the water, but water has 2 lone pairs. So one lone pair, the hydrogen ion will hook up to one of the lone pairs. So when that happens, now you got 3 hydrogens in the water molecule. So H3O plus is the H3O plus. All right. Now, and the Cl minus by itself. So you got separation of charge in solution. All right. So that's the acid-base type of reaction there. The water is the base, and the acid is strong as HCl. Here's another one. Acetic acid, this is the acid found in vinegar. So you see it's going to donate the hydrogen ion. The hydrogen to the extreme left, that is the acidic hydrogen. None the H3, none of the acidic hydrogen. The acidic hydrogen is that one hydrogen there. That's the one we're talking about. So the vinegar is going to donate the hydrogen to the water to do the same thing that I did in the first reaction. H3O plus, and that's so it's the dissociation is -1. I mean, because as acetic acid is weak, so it does not give away most of the proton. It's stingy with the proton, so it's what negative. I mean, just 1% dissociation. This area is very important. So the H3O plus is called a hydronium ion. Hydronium ion. It's formed when a hydrogen ion attaches to a non-bonding electron pair on a water molecule. Now the water molecule is as you saw the water molecule before, which is a bent molecule. All right. And the geometry is tetrahedral. It has 2 lone pairs. Now, ammonia has 1 single lone pair. All right. So that's why the angle, we saw the angle was 107. All right. But water has 2 lone pairs. So the tetrahedral angle, 109.5. Let me jog your memory. The tetrahedral angle, when something is neutral and a tetrahedral, like methane, for instance, we see that the angle is 109.5. Ammonium, nitrogen has a lone pair sitting on there, so that will reduce the angle from 109.5 to 107. Water has 2 lone pairs, so therefore that even reduces the angle further from 109.5 to 104. Okay, so therefore that caused the water molecule to bend. So the shape of the molecule, water molecule, is bent shape, but the geometry is tetrahedral. We discussed all that. Today's the last day, so I'm jogging your memory. You see, remember that? Do you recall? Do you recall? Do you recall? And after this class, I will never see some of you anymore. Maybe I might even pass by you in the street. You even know who I am. And but I'm Dr. Tukwi, your chemistry teacher. 2020 summer. All right. So we see here strong bases. Now we've been talking about acid. Now we come to the bases now. Bases will dissociate extensively to release hydroxide ion, which is a polyatomic ion. It's not very soluble, but if it's attached to, when you go to solubility table, sodium, lithium, those things there, it becomes soluble. So when you look at the solubility table, you notice that hydroxide ion is not very soluble. But if it makes the attachment to group 1, which is what? Lithium ion, sodium ion, potassium ion, ammonium ion. If OH is attached to this thing, it's going to be soluble. All right, we discussed all that. Weak bases only ionize slightly in solution. If they are weak, they're very stingy with the OH ion. Stingy. All right, so they just give a little bit away, just like the acid. When the acid is weak, they give away small H+, very stingy with the H+. Bases are stingy with the OH- if they are weak. But they are generous, they're 100% when they are strong. So there's the same concept. So look at table 14.3. Barium hydroxide. Remember I said I went to research there are 8 strong bases. At the end of this class, I will come back and find out if you found the other acid, strong acid, and other strong bases. Okay. So barium hydroxide is a strong base. It's will dissociate 100%. Calcium hydroxide is a strong base, 100%. Lithium hydroxide, 100%. Potassium hydroxide, 100%. Sodium hydroxide. Now, look what you notice. If you look at lithium, potassium, sodium, they are in group 1. All those are group 1 metals, all right? Look at calcium and barium, they're in group 2. So that's one way to remember this stuff. Of course, that ammonium ion is a unipositive atomic ion. It's not, you can't find out on the periodic table, but it's a polyatomic ion. When we study the language of chemistry, if you can recall, NH4 plus was the only one. How did it get to be that? Because through the concept of coordination, ammonia has one lone pair, excepting hydrogen ion makes it NH4 plus. Ammonium hydroxide is prepared by dissolving ammonium gas in water. Ammonium gas in water. Okay? It is referred to as an aqueous ammonium solution. Whenever you hear the word solution, what comes to your mind? Solvent comes to mind, solute comes to mind. NH3, or ammonium water. All right? The name ammonium hydroxide is somewhat misleading since there is no evidence for ammonium hydroxide, no evidence. It's misleading, but we'll call it anyway. Molecules in a solution. All right? So for simplicity, however, we refer to ammonia solution as ammonium hydroxide for simplicity. So this is as vital. All these solutions, you will find the pH. You got to know how basic it is, how acidic it is, and so on. All those, the pH meter is very important. But when you're out there let's say outside the lab, outside of where electricity is, unless you have a pH meter that run by a battery, then you use a litmus paper to test to see it's acidic or basic, but you don't know exactly. If some of the litmus paper got a range, you can look, compare and see this is 7, this is 5, this is such and such. All right. When we dissolve a hidden bases in solution, they dissociate, giving a cation and a hydroxide anion. Strong bases dissociate almost fully, and weak bases dissociate very little. All right, so the hydroxide is a strong base, so it's 100%. All right, on the solubility table, sodium is in group 1. Solubility table, so anything attached to that, we say, is going to be soluble. All right? Alkali metal, so 100%. Ammonium hydroxide, stingy with the OH ion, 1%. All right, so these things, recoil. You see the word recoil again? It's telling you that we talked about these things before. That an acid neutralizes a base to produce a salt and water. HCl. Now, look at this. HCl is a strong acid. Sodium hydroxide is strong base. So therefore, the salt that we make here is a neutral salt. NaCl is a neutral salt coming from a strong acid and a strong base. Remember I told you earlier that when the base is strong and the acid is weak, that's the basic salt. When the acid is strong and the base is weak, that's the acidic salt. But when both acid and base are strong, you have a neutral system. The reaction produces the aqueous salt, sodium chloride. If we have an acid with two hydrogens, like sulfuric acid, it has two hydrogens in it. We need two hydroxide ions to neutralize it. All right? The first hydroxide ion will pull away the hydrogen ion. The second one will pull away the next one. So that's what you see there. So you need two sodium hydroxide to react with 1 mole. So now 1 mole and 2 moles of this will give you 1 mole of salt and 2 moles of the water. All right. Now, we can identify the amino acid and base that react in a neutralization reaction to produce a given salt such as calcium sulfate. Now, here's what I would do. If you're in if we're in a setting, I should have given it on the final exam. I'll give you the salt, okay, and then tell me, or walk backward. Tell me which acid-base reaction will give you the salt calcium sulfate. Okay, now I'm going to start and ask the question. We got calcium sulfate. Can somebody tell me what acid-base reaction give you that salt? Anybody? What acid and what base will react to give you calcium sulfate, which is a salt? Is anybody there? Or should I call the names? I'm going to call names. Okay. Claudia? Can you tell me, Claudia? From group 6? All right. I'll go to group 3. Tiffany? Can you tell me which acid and which base will react to give you calcium sulfate? All right, I'll go to Cynthia. Cynthia? From group 4?
Hi, Professor. Yes, I'm here.
Can you tell me which acid and which base will react to give you calcium sulfate?
I've got to think about this.
Okay.
Let me see.
Professor?
Yeah?
This is Shella from Group 9. Would it be sulfuric acid and lime?
What is it now?
Sulfuric acid and
what?
The base. Sulfuric is the acid and then lime is the base.
So what is it? What is the chemical name for this?
Hydrogen.
Can you please repeat the question?
The question was, which acid-base combination will give you calcium sulfate? No.
Would it be the sulfuric acid and the calcium hydroxide?
Very good. It's right there on it. Are you not looking at it? H2SO4, calcium hydroxide. So the base is calcium hydroxide and H2SO4. Everybody see that? That'll give you calcium sulfate. So now I will in regular setting, I'll give you a whole bunch of salts and I say walk backward to the reactant. Find the acid and find the salt that'll produce that. Find the acid and the base that produce that salt. All right. So you know that sodium chloride solutions conduct electricity. Now this guy I was just talking with India this morning. We have next chart. Now, India, pay attention to this part now. Here's a guy right here.
Okay.
This guy is doing dissertation. We were just talking about dissertation this morning. So he's the guy who discovered that there were ions in solution. All right. He noted that sodium chloride solution conducted electricity. So whereas sugar solution did not. All right, he noticed that. He also noticed that the freezing point of sodium chloride solutions were lower twice as much as sugar solution at the same concentration. So therefore, he wrote a proposal. A proposal that sodium chloride produces ions when dissolved, whereas sugar was in solution as, whereas sugar did not in solution. Sugar was a molecule in solution. It did not make ions. So he made his presentation. He was doing a dissertation. So 4 or 5 hours he's sitting there talking to people that had no idea about what ions in solution is. They had no idea. So they gave the guy almost failing grade, gave him C, because they didn't know. All right? So what happened is 20 years went by after this guy gave his presentation. It was nearly 20 years before his idea were accepted by the scientific community. Do you see that? So don't feel bad. Don't be discouraged when you're telling people that this is this. And because they don't know about it, they will tell you no. And then later on, after they're all dead, then the people come to find, oh yeah, like she was right or he was right. So it's not easy to convince the scientific community. It's very difficult. You right now, that's one of the reasons why they having a hard time finding the vaccine for this virus. Because each person want to take the credit, want to do the Albert, trying to get credit for this thing. If whoever finds this thing, that's a lot of money they're going to get. All right, so 20 years went by. All right, so we see, so that's his story. Now here are 2 guys, one in England, one in Denmark. Sometimes you have 2 guys in different places, don't even know each other, doing the same thing, have no idea. And then when they present themselves together, if they present together, then they both get credit. So Brunstelle, Lorentz definition of acid, they're also working on acid-base types situation. And bases are broader, they have a broad definition for what ahinians have. Ahina is that anything that is a base must have an OH ion in it. Anything that's an acid must have an H+, okay? So that the definition is very narrow there, narrow definition. But these guys are saying that there are some substances, they don't have to have an OH in it, but they are still bases. That's what Brunstelle and Lorentz. Acid is a substance that donates halogen ion as well to any other substance. That substance does not have to have an OH ion. That was their research. It is a proton donor. A Brunstelle base is a substance that accepts a hydrogen ion. It is a proton acceptor. So that was it. Definition for the thing that the other guy was doing. So let's look at this. Brunstelle and Lorentz, continue here. Let's look at the 2 acid-base reaction. The first one, fine, with ahinians, because sodium hydroxide has OH in it. So that's fine. It worked for all of them. The second one, the NH3 has no OH in it. So it cannot be ahinian's base. Do you see the difference now? it does not have an OH in it. It has a lone pair sitting on the nitrogen. So according to Brewster and Lurie, that because of that lone pair serves as a base. Make this species a basic species. It can accept hydrogen ion from the acid. So their definition is as long as you can accept hydrogen ion, any species that accept hydrogen ion, that species is the base. Ahinian is saying to be a base, you gotta have OH. So their definition is broader than the Ahinian. Brewster and Lurie. They have a broad definition. They accept what he's saying. They agree with what he's saying. Because OH is a base as well. They accept that part. But beyond the OH, anything that has a lone pair, that's one of the reasons why the water molecule has two lone pairs. Remember that reaction? It had a hydronium ion. That lone pair accepted the hydrogen ion coming in. So that would be a Brewster-Lurie type situation. So the NH3, because it has a lone pair sitting on a nitrogen, it will accept the hydrogen from the hydrochloric acid. So therefore, you got what? NH4 plus. This is how the NH4 plus was generated. So now you see, therefore, you don't have water in this acid-base reaction. There's no water present here. It's just a salt. When it's salt, no water there. You see that? HCl donates a proton in both reactions. Yeah. And it is a Brewster a little bit. So HCl is donating proton to both. So that's Brewster-Lurie acid. Okay. In the first reaction, the NaOH accepts a proton and is a Brewster-Lurie base as well. They accept that because it's accepting the proton. But in the second reaction, take a look at the second reaction. NH3 is a base. That is not Ahinian's base because it does not have an OH ion in it. Do you see what's going on here? You should be able to distinguish on a final examination. Give you so many bases, so many acids, can you identify which base is Ahinian's base? All right. Accept the proton and it is a Brewster-Lurie base. So you should be now the Brewster-Lurie concept is big in organic chemistry. When you take organic chemistry like 66, it's big there. It's big in beyond higher organic courses. All right. The lone pair turn out to be a base. Anything that is, all right. So substance that is capable of both donating and accepting a proton is an amphiprotic compound. All right, watch that now. Substance that is capable of both donating and accepting a proton is an amphiprotic compound. Okay, so there you are. You can accept money from somebody and you can give money to people. There are people, there are organizations, foundations, they collect money from people, all right? And then they give money out to people that are doing something else. So they're amphiprotic. Amphiprotic, all right? Take the money, but not the one that takes the money, don't give it away. You're not amphiprotic. So amphiprotic, so your parents are amphiprotic. They go to work, they get paid. Then when they give them the money, they take that money and spend it on you. So they are amphiprotic people. That's why you should love them. You should respect them. Your parents are amphiprotic. And you are now getting there to be an amphiprotic sooner or later. So we see sodium hydrogen carbonate. Sodium hydrogen carbonate. Baking soda we dealt with in a reaction. Okay? Sodium hydrogen carbonate or sodium bicarbonate is the same baking soda. So, take a look at baking soda. When baking soda is in the presence of a strong acid, it will behave like a base. All right? That's an example of an amphiprotic. But sodium hydroxide and sodium bicarbonate or sodium hydrogen carbonate, if it's in the presence of a weak base, it's going to behave like an acid. Or strong base, see, strong base, it can behave like an acid. So here we go, look at the first reaction. Sodium hydrogen carbonate is in the presence of a strong acid. So now it's going to be the base. If it's in the presence of a strong base. All right? So therefore, because of that, and it becomes the acid now. So in a second reaction, it is the acid because it has a proton in the middle there, proton. It will react with the sodium hydroxide to give you sodium carbonate and give you water. Okay? And it's supposed to give you carbon dioxide too. All right. So, look at the first reaction. The same material, sodium hydrogen carbonate, is in the presence of a strong acid. So now you're going to have what? Salt and an acid. Okay? So these are, so NaHCO3 except a proton for HCl in the first reaction and donates a proton to sodium hydroxide in the second reaction. So that's amphiprotic, just like your parents are. Your parents are amphiprotic. They go to work. They work for somebody. They take all the abuses from people because they have you to take care of you. So now they bring the money home. The mother goes shopping for food. They pay the mortgage. They do all these things here. That's amphiprotic. All right. So here we go. We're talking about pH. Go back to pH now. Acid base. Any questions so far, anybody? A solution that is sensitive to a change in pH by exhibiting a different color is an acid-base indicator. Very sensitive to a change is an indicator. And when you're using the indicator will tell you, you know, when you got the titration, remember that? We did a KHP and the sodium hydroxide. You use a phenolphthalein indicator. All right? And when you get to the endpoint, the color will change, and color change will be permanent. I don't care how much you add there, you know, it passes that point anyway. So that's the indicator. Shown below are the three indicators at different pH values. All right, so you got pH 2, pH 4, indicator 5, 7, 9, and 10. 2, 4, 5, 7, 9, 10. 2, 4, 5, 7, 9, 10. All right, those are indicators. The pH value, so there's a solution as well. So you take the pH and say, okay, So the one that has the pH 2 is very acidic, very, very acidic. pH 4 acidic. Yeah. They're getting that 7 neutral. 9 is basic, 10. Then the basic. Remember we say on the pH scale from 1 to 14. 7 is neutral. So these are things that you use to flag you down, indicate or let you know. Titration, this is what you did already. Look at definition of titration. You don't know that before the final. A titration is used to analyze an acid solution using a solution of a base. A titration is used to analyze an acid solution using a solution of a base. All right, is that correct, Sheila Marie?
Yes, Professor.
Okay. A measured volume of base is added to the acid solution when all of the acid has been neutralized. All right. So, is that correct, Jessica? All right. And is that correct, Camille?
Yes, Professor.
All right, 1 extra drop of base solution after the endpoint increases the pH dramatically. One drop will change things. That's one of the reasons why when you're doing a titration, we use in a lab setting, actual lab setting, we use bottle of water, you know, to wash the tip of the burette, so you can't put too much on there. Okay, squeeze bottle. When the pH increases about 7, phenolphthalein changes from colorless to pink, and I think you guys saw that, indicating the endpoint of the titration. I mean, I don't care what you add there, you've gotten to the endpoint, and the change of color must be permanent. Okay, so here's what you did. The beginning and middle and the end of an acid base using phenolphthalein as an indicator. This one here, you added the indicator there, but you have not added anything with respect to the base. The indicator itself is the acid, so there's no color change when you put that in there. As you open the stopcock, this is a stopcock, you gotta use that, stopcock. You open the stopcock, the base begin to drop in. You begin to see some color, you gotta shake that, you know. You have a pH probe in there. And when you get over here, you got to the end point now. To me, if you're in a lab setting, I think, this is too loud for me. You gotta be very faint and permanent. Faint and permanent. All right? To get a really great result. All right. So there's a titration here. And this is something that you did in the lab. So let's consider titration of acetic acid with sodium hydroxide. Acetic acid is a weak acid. Sodium hydroxide is a strong base. So it's an acid-base reaction. So the salt that will generate in the process will be a basic salt. So a 10.0 milliliter of sample of acetic acid. After the titration, you measured the burette is 37.55 milliliter of zero. This is the concentration of the molarity of the sodium hydroxide. So volume times concentration give you moles. So the first thing you do is to write a balance equation. That is the first thing you do. So when the balance equation will tell you how many moles of each of those species, reactant and product. So we notice that the equation is balanced. This is acetic acid, the one found in vinegar that made vinegar sour. This one right here. This is sodium hydroxide, all right, strong base. So this is a salt, sodium acetate. Sodium acetate is a salt, all right? Sodium acetate is a salt plus water, salt plus water. Okay, so we want one concentration of acetic acid. We want how strong this acid is. That's our goal. We're doing this, all this work at a titration to determine how strong this is. So now, concentration NaOH goes to mole. How do you get mole? When you multiply, now this is in milliliter. The volume reading from the burette is in milliliter. But the concentration molarity is moles per liter. So you got to change this here to liter so you get moles. So the number of moles you get from this, you got a ratio of acetic acid and sodium hydroxide is 1:1. So the number of moles will be the same. Number of moles will be the same. All right? Okay. Now, so the molarity of the sodium hydroxide can be written as a unit factor, molarity, which is moles per liter. Okay? So because the burette is delivering volume in milliliter, so we gotta complement this here and change the moles per liter, which is the molarity, to what? Moles per 1,000 milliliter. To accommodate the milliliter from the burette. So this is a 37.55 milliliter of solution. All right, this is a sodium hydroxide solution in the burette. Here is the concentration of what's in the burette. All right, so because this is in milliliter, now pay attention to this. This is the stuff you got on your final examination. Milliliter of solution, milliliter of solution. We got to change this liter to 1,000 milliliter. All right, so therefore, milliliter solution drop out, so now we got moles. Moles, you multiply this by this, you get mole. It's in mole now. So where does this factor come from? This factor comes from the balance equation. All right? It's 1:1 ratio, 1:1, one more of this to one more of that. Okay, so therefore, we got 0.00837 moles of the acetic acid. All right? Which is the same as the, all right, of the base in the burette. So you got, that is 7.55 times 0.233, divide that by 1,000. And what do you have? Okay, it's the same thing because the ratio is 1:1. The ratio is 1:1. So now we know that the number of moles of the sodium hydroxide is the same as the acetic acid. Now, what was the volume of the acetic acid we used? We took we used 10.0 milliliter of the acetic acid solution. So the concentration is moles per liter, right? But we got to convert the 10.0 milliliter of solution to liter. So multiply that by 1,000 milliliter of solution over 1 liter of solution. So now the concentration, so let's say you went to the store, you bought a bottle of vinegar, okay? And you wanted to know what is the concentration of the acetic acid in the vinegar you bought. Maybe they have mass percent on it, but you want to know that you can convert a mass percent to molarity. That's what you're going to be doing in final. Change the concentration in mass or in molarity. Any questions so far about this problem? Anybody?
For the second part, why are you dividing by 10 milliliter solution?
No, you took 10.0 milliliter of the solution in a flask. Okay, let's go back. You see here? Let's say this is the 10.0 milliliter in here. You see that now? This is your vinegar solution right here. Acetic acid is in there. So now you're going to titrate up to here. This is where it came from. You got that now?
I got it.
You got it now? So you need a material. I don't care how much water you add to this, you still got to work with a 10.0 milliliter. It's just like taking salt and putting the salt in the soup, right? And he said, the soup is so salty. So you add water to that. I don't care how much water you add there, the value of salt will not change. You got that now? So therefore we have this is a concentration of this right here. Any question on this, anybody? The exam is tomorrow.
Just to clarify, that 10 milliliters, it was given, right?
It was given, yeah.
Okay, all right, thank you.
Yeah. All right, so tomorrow is the day. I won't be there. I'll be cheering you on. All right, so here we go. A 10.0 milliliter sample, that's given a 0.555 molar of H2SO4. Is titrated with 0.233 molar NaOH. What volume of NaOH is required for this titration? You see it different now? It's the problem. So we don't know how much coming out of the burette. The previous problem, we knew how much came out of the burette. See? We knew we had 37.55 milliliter what delivered from the burette. But in this problem now, the one you got, you do the concentration, and let's go back again. We knew what coming out of the burette, but we did not know the concentration of the acetic acid. So this problem is the opposite of the problem that we're going to be looking at now. We did not know the concentration of the acetic acid, but we knew how much we deliver from the burette, and we knew the concentration of what is being delivered from the burette. All right? Well, look at this problem. Look at this one. We know the acid concentration. We know how much it is, and we know the concentration of the base in the burette, but we don't know what will cause the color change when the titration is done. What caused the endpoint? You see the difference in this problem? So we don't know. So then the question is, let's figure out how much before we even start a titration. See, this problem says, look, do the calculation first before you even start a titration. So now you know how much you're going to deliver to make the color change. So now, gradually, you got to do it slowly until you get there. Isn't that nice? All right, we want ml of NOH. That's what they're asking for. Hello? How much are we going to be delivering? We figure out first. Do not do the titration. Figure out first before you start. We have what? 10.0 milliliter of H2SO4. We know the concentration of H2SO4. So therefore, we'll write a balanced equation, number one. Start with a balanced equation. So you know the ratio. Start with balanced equation, number one. That's key. In all these problems, write a reaction and balance the reaction. Here we go. Here's, see why it's important? So look at the ratio. 2 to 1 is 2 to 1 because the H2SO4 has two hydrogen in there. So you need 2 hydroxide to balance that 2 hydrogen from the acid.
Professor?
Yeah?
So for the ratios, you always look at the number in front of the
The coefficient, yeah.
Yeah, oh, the coefficient, yes, okay.
The coefficient, which is, could be molecules, could be volume, could be mole, right?
Yes.
No, so the ratio is, sulfuric acid is 1, and the hydroxide is 2. So it's 2 to 1, or 1 to 2. You see that now?
Yeah, I see it, thank you.
So we're going to set this up, 10.0 milliliter of the acid, start with that, and followed by H concentrate, just like we did the first problem. When we get here, see why it's important that you balance the equation? That factor, 1 to 2. We want 1 to 2. So you got to have that. So you can't assume anything. So now that factor goes, this factor comes from the balance equation. 1 mole of H2SO4 to 2 moles of sodium hydroxide. So now, from the burette, we're going to deliver 49.8 milliliter. So now when you pour in the sodium hydroxide in the burette, you just pour. When you get a 40, they start going slowly. You're almost there. Then you start whistling. Having a good time. Until when you get to 49.8, bang, the color change. Right there. Don't go beyond that again. The color already changed permanently. Don't go beyond that. You've done a good job. So in this problem today, do the calculation first before you start the titration. Balance the equation. Any question on that? Typical exam question. So you got to write a reaction first. Set up the factors. So 49.8 milliliter of 0.233 molar NaOH is required to neutralize 10.0 milliliter of 0.555 molar H2SO4. So you're in the lab setting, you're working for some company, working for yourself. Whatever you're doing, you gotta make sure you do this stuff. All this should be in your lab book. All this, every scientist working in the lab, you need to have a lab book. Lab book, when you're leaving, let your lab book be under your arm. Do you know scientists have killed each other for that lab book? This is no joke. Because somebody trying to take your credit. So you make sure you keep that lab book. Okay, so you have that. So now you know how much you need to pour for the burette. Let's talk about standard solution. You did that before. standardization. It's so important. That is a precise way of figuring out the concentration of something. You're being very precise when you do standardization. I think I told you that when I worked for Firestone as a student from the university, during the summer, I do all my standardization on Friday for the week. Every Friday, I check to see if the concentration is still holding. So I do my standardization. All right? So it's very, very important. I wanted to make sure, I want to be precise that the concentration is still holding there. It's still holding tight. So if I don't standardize, I will not know. So I got to standardize. So it's a solution in which the concentration is known precisely. Do you want to know your concentration precisely? Then you got to standardize. You got to standardize. That's what you did that for. You got to have that exercise. Acid solutions are standardized by neutralizing a weight quantity of a solid base. All right, solid base, which is if you try to standardize the acid, sodium carbonate is the base you're going to be using. Now, in your case, you use a KHP because you're trying to standardize a base. So depending on where you're trying to standardize. You cannot use KHP trying to standardize acid, but KHP is the acid itself. You can't use acid to standardize acid. You got to use base to standardize, acid. You got to use acid to standardize base. See, so keep that in mind. Any questions so far? Anybody? The acid solutions are standardized by neutralizing a weight quantity of a solid base. What is the molarity? Moles per liter of a hydrochloric acid solution. They're asking for the concentration now. The question is, what is the molarity? Bang, right away. They're asking me for the concentration, which expressed in moles per liter of the hydrochloric acid solution. If 25.50 ml are required to neutralize 0.375 gram of sodium carbonate. So you go, you weigh sodium carbonate. Dissolve that sodium carbonate. And you're going to do the titration. All right? That's what you guys did. You use KHP. You weigh the KHP, then you dissolve the KHP, and the sodium hydroxide is in the burette. You're trying to figure out what is the concentration, and you did at what? 3 samples, then you take the average, or in your case, there's do 5. I found the 3 that are so close by. If you did a lab, or you all did a lab, now if you did, you're supposed to find the 3 that are close by, take the average of the 3, and that concentration will be given to the sodium hydroxide, which you did. I'll be expecting that in your lab report. Tomorrow I'll be grading lab all day long. Tomorrow, grading lab, while you concentrate on the exam, I'll be concentrating on my lab, grading lab. So we'll all have something to do tomorrow. So, but no, in all cases, you got to write a reaction. So the HCl and the sodium carbonate. You got to write a balanced equation. The ratio is 2 to 1, 2 to 1. See 2 to 1 there? All right, the reactants. We got the reactant, 2 to 1. So now we're going to start. We gave you 0.375. Start with what's given to you. What do you want? All those steps. One more of, so you find this is in, whenever you see grams, start thinking more. More comes to mind. All right? So you have gram of sodium carbonate. One more of sodium carbonate weigh how much? That 105.99 comes from the periodic table. You got 2 sodium in there, you got 1 carbon there, you got 3 oxygen. You go up to the periodic table, out of all those weights, you got 105.99. I want everybody to try that now and see if you get it. Everybody try that. Find the molar mass for sodium carbonate. Look at the periodic table. Let me give you 5 minutes to do that. Everybody get involved. Find out how they got 105.99. And let me know, is that correct? All right, who got it? Everybody got it?
Yes.
Very good. All right, so now we have that. So this factor comes from the molar. This factor comes from the balance equation. That's why it's so important that you balance the equation, 2 to 1. So you get number of moles. But we are looking for the concentration of the hydrochloric acid. So now that we got a mole, you're gonna, and what was the volume of the acid solution? 45, 150. So you express this number over that moles over volume. But the volume is in milliliter. And molarity it should be in liter. So now we're going to multiply it by this. 1,000 milliliter of solution to 1 liter of solution. So here's the concentration that your supervisor, you report it to your supervisor, 0.277, if that is correct. Now, I want you to check this out. Go from here to there, see if you get 0.277. Everybody, try that. Check that and see if you got 0.277. It's a practice for the exam. You got, okay, 0.277. That's the A or B or C or D or E, you know.
Professor, I got it. I just did the calculation. I got it.
Very good. Very good for you.
Got it down as well.
Very good. All right. So occasionally, once in a while, occasionally, 2 water molecules react to produce a hydrogen ion. 55 million of water molecule. A 2 water molecule is a network, huge network. And only 1 water molecule can be detached at a time. 1. So occasionally 2 water molecules react to produce a hydrogen ion. So you got 2 water molecules. So one of them become an acid, one behave like an acid, one behave like a base. 2 weak bases, 2 weak. So what is amphoteric? All right, it behaves both like acid and base. So we see that you get a hydrogen ion. So this, So one behave like a base, one behave like an acid. The one that is an acid is donating the proton. The base is a proton acceptor. Base will accept the proton. We just discussed two group of people, all right, in our business. Only about one, now listen to that. Only about one in 500 million water molecules. Only about one in 500 million water molecules is present as an ion. 500 million water molecules. You see the hookup? That's a network. 500 is the hookup. How they hook up? Hydrogen bonding. Hello? Hydrogen bonding, remember that? Hydrogen bonding, the special dipole. They hook up in terms of hydrogen bonding. You get only one water molecule can be released from there. So the concentration of water ion, hydrogen ion, see that bracket you're looking at, what does that bracket mean? It means concentration is expressed in moles per liter. Every time you see that hydrogen ion in that bracket, the bracket stands for moles per liter. Everybody see that? Moles per liter. In pure water, it's about 1 times 10 to the 27 moles per liter. Now, do you agree with that number? How many think that thing is right? 1 times 10 to the 27 in pure water. All right, I'll check you out. I'll come back. Since hydrogen ion is 1 times 10 to the 27 at room temperature, the hydroxide ion concentration must also be, now, do you see that now? Everybody see that? Do you agree that they made an error there? All right, we'll look at the pH now. pH has go from 1 to 14. So look at it, say, the hydroxide ion concentration OH must also be. What does that mean, that language? Must also be equal to the same thing. But are they equal to the same thing? No, they're not. All right, so therefore you got this. H plus will dissociate to H plus or H minus. At room temperature, the two of them, each one is what? 1 times 10 to the 7, and not 27. 1 times 10 to the 7, this person want to lunch on that. 10 to the 7, 10 to the 7, I'll give you 1 times 10 to the negative 14. This is the ionization constant for water. KW, standing for ionization constant for water. All right, so therefore we have at 25 degrees C, which is room temperature. So you see the hydrogen ion in bracket, OH ion in bracket. There you go, 1.0 times 10 to the negative 14. So if we know the hydrogen ion concentration, we can calculate the OH ion concentration. So what is the OH ion concentration if H plus is 0.1? All right, take a look at that. Now substitution, the question says, what is the OH ion concentration if H plus is 0.1 molar? So in place of H plus, you put 0.1. OH, you solve for OH. So algebraically, you should get what? OH to be 10 to the negative 13. Everybody see that? See how that is done? Now I want you to memorize the log of 2 and the common log of 2 and the common log of 3. The log of 2 is 0.301. The log of 3 is 0.477. All right, we'll check that out and see. All right, so here we go. Recall the pH. We talk about pH a lot. Now we're gonna see an expression, a mathematical expression for pH. Is it a measure of the acidity of a solution? A neutral solution has a pH of 7. That means there's no base, there's no acid, it's neutral. And the basic solution has a pH greater than 7. pH less than 7 is acidic. All right? Neutral will be 7. Acidic will be less than 7, and basic will be greater than 7. So the pH scale uses the powers of 10 to express the hydrogen ion concentration. All right, mathematically, take a look. pH is equal to what? Negative log of H plus concentration, which is expressed in moles per liter. Write that down. If you need that on the final. pH equal to negative log hydrogen ion concentration. Okay. Yeah.
Can
You got it?
No, can you say it one more time?
The pH equals to written right there. You see that? pH equal to negative log.
Okay.
You see that formula there?
Yes.
Yeah. That's what you need to write down.
Okay. Thank you.
What is the pH of the hydrogen ion concentration? E vinegar. Solution is 0.001. What would the pH be if the hydrogen ion concentration in vinegar is 0.001 moles per liter? So you write down pH equal to negative log of H plus. Now let's do a little review here. The log of A, the log of a product, that's it. The log of A times B is equal to the log of A plus the log of B. Write that down. The log of a product, like A times B, will be the log of A equal to log of A and log of B. The log of a quotient, the log of A divided by B, will equal to the log of A minus the log of B. The log of an exponent, like, what is it? The log of A to the n power. It will be written as the log n times the log of A. Anybody who didn't get that? Let's check you out. The log of a product, the A times B, will be the log of A and the log of B, plus the log of B. The log of a quotient, the log of A minus the log of B. Okay?
Professor, can you repeat the last one?
The last one is log to A to the n power, right? Equal to n times the log of A.
Okay, got it. Thank you.
You got it now? So the pH of 3, so what we do, just move the decimal point 3 places, they become 10 to the negative 3. So therefore, the pH of a vinegar is 3, so the vinegar is acidic because it's between 1 and 7. All right, if we rearrange the pH equation for H plus, so now we give it a we gave the pH. We said pH equal to negative log H plus. So how about the H plus? How can we use that same equation to solve for H plus? All right. So here we go. So H plus is equal to 10 to the minus pH. Write that down as well. H plus concentration because sometimes they'll give you the pH, and they'll be asking for the hydrogen ion concentration. Milk has a pH of 6. All right. So what is the acidic hydrogen ion concentration in milk? So what another acidic hydrogen ion concentration? So you say your equation, hydrogen ion concentration, you're going to 10 to the negative pH. 10 to the negative pH. Milk has a pH of 6. What is the concentration of hydrogen ion in milk? So there you write down H plus concentration. You're going to 10 to the negative pH. So that means 10 to the 6. What is 10 to the 6? How many zero? 1, 2, 3, 4, 5. Then I'm put a 1 in front of the move the decimal point all the way to from the 1. So that'll be 10 to the 6. So the concentration is 0.00000. So it's very minute. It's pretty too close to 7. So it's not that much in milk. If the pH is 6, the hydrogen ion concentration in milk is very, very small. Any question on that? Anybody? This is part of the exam reviewing now. This part, so pay attention to this part right here. All right. You got to solve the problem before you say A and B. Or if you go guess. Yeah. Any question? All right. What is the pH of blood now? Those of you that are going to be in the hospital setting, you need to know this. And some of these are not right. They're not correct. We're going to correct them. And let me know if it. So, what is the pH of a blood with the hydrogen ion concentration? 4.8 times 10 to the negative 8. That's one of the reasons why I give you that log of product. Log of product. Log of AB or A log of A plus the log of B. So now you got 4.8 times 10 to the negative 8. That's like saying A times B. Look at it, 10 to the negative 8. That's like saying log of A to the n power. So you got mixture of two of them there. The product and the logarithm. So now you have that. So here we go. The pH, so you got to write the formula first. pH, you got a negative log of the hydrogen ion concentration. So in the bracket, you put on 4.8 times 10 to the negative 8. All right? So you're going to have to solve the problem. You got to see the log. So negative log of 4.8 plus negative log of 10 to the negative 8. Then you change that to the negative 8 to what? Negative 8 log of 10. So you got two things you got to do in that problem. I want everybody to try that problem and see if you get that same result. I'll give you 5 minutes to try that problem. See that result is correct. Let me know if it's correct. How are we doing with the first problem?
I'm not getting that.
Yeah, me neither. I'm not getting that either for the first one.
I'm getting 7 something.
What is it now?
I don't know. I'm not getting that either.
I'm getting like 7.32.
Very good. Let's celebrate that.
Oh, so it's wrong.
They are wrong. It's not 3.82.
Okay, I was going crazy over here.
Do you see that? What is the log of 4.8? The log of 4.8 is 0.6812, something like that. Did you get that?
Yeah.
No.
Yes.
The log of 10 to the negative 8, so negative log, so it'll be positive 8, and the log of 10 is 1. So when you add is negative 0.6812 to 8, you get a 7.31, 88, and you round up to. You see that now, Albert? See that? Who's still not getting it? That's one of the reasons why I say the product. This is a two-part problem. The product, and then the exponent. The log itself is the power itself is the log. So did you get what she got? Who got 7.3? 2.
I did.
I did.
Yeah.
What's your name?
Chanel Marshall.
Chanel, Masha, and
Cynthia.
And Cynthia. All right. Okay. Everybody see that? Anybody else didn't get what they got? What Chanel and Cynthia got? Who? Because this is an exam question right there.
I got the same thing as them.
You got the same thing? Everybody getting the same thing?
I got the same.
That's good. All right, now let's move on to the second one. What is the hydrogen ion? It's a reverse now. In orange juice, you got orange juice. You wanted this to end, but orange juice, and they give you the pH to be 2.75. So you want to know the hydrogen ion in there. We're gonna use the hydrogen ion equation. Hydrogen ion equal to 10 to the negative pH. Okay? So what do you do with this one? Anybody have an idea? Okay. 10 to the negative 2.75. So in this problem here, you're going to 2.75 is close to 3, right? So you're going to subtract the 2.75 from 3.00. What do you get when you do that? $2.75.
0.25.
0.25, yeah. Okay. So now you're going to find this is reverse. So the reverse is called anti-log. Anti-log. So you're going to say the anti-log of 0.25 is equal to 10 to the 0.25. To find out 10.25, what does that give you? Use the 10 to the x function on your calculator if you have that. What do you get when you do that? And then, so whatever you get, you're going to multiply by 10 to the negative 3. What did you get when you did that?
Okay, so what I did, I just did 10 to the negative 2.5, and then I got 1.77 to the negative 3 power.
Times 10 to the negative 3.
Yes.
Okay. Look at what they got. You don't have it right. You see that there?
Yeah, I see it.
Yeah, it's wrong there. All right, so those are some of the mistakes I told you. I say that some mistakes in this video, watch for them. So this is what we call the anti-log. Okay. So now we have, see what ACID can do? This is your critical thinking. When people don't know what something can do, studying material is very, very important. Nitrogen oxides, sulfur oxides produced from the combustion of fossil fuels. We have brown fossil fuel react with rainwater. We call acid rain. Have you heard of acid rain before? Anybody? Acid rain to produce nitric and sulfuric acid. So these strong acids reduce the pH of rainwater. So take the pH down from 7 going all the way down, 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 down. Acid rain refers to rain with a pH of 5. So when you get rainwater, you test the pH of that rainwater or below. That's acid rain. Okay? pH of 5 or below. That's considered acid rain. All right? If it's above that, that's not acid rain. Acid rain can cause corrosion. Take a look at George Washington. All right? Metal and degradation of limestone, calcium carbonate, limestone, and marble salts. So that's what happened. Now, an aqueous solution that is a good conductor of electricity is a strong electrolyte. This is what a guy did when he told the people there were ions in solution and they didn't believe in it, gave him C grade. And about almost 20 years before they found out the truth about what he was doing, Arrhenius, we talked about that this morning. There's a stuff that he was doing. The aqueous solution that is a poor conductor, electricity is weak electrolyte. Now strong. So in the medical arena, nurses you'll be hearing electrolyte all the time. The greater degree of ionization dissociation is the greater the conductivity of the solution. So if you put sugar water in here, it will not conduct electricity. All right, but salt water will. Okay. Weak acids and bases are weak electrolytes. Strong acids and bases are strong electrolytes. So weak acids and weak bases are weak electrolytes. Strong acids and bases are strong electrolytes. The sodium hydroxide and hydrochloric acid, they give you salt, neutral salt. Insoluble ionic compounds are weak electrolytes. Soluble ionic compounds are strong electrolytes. So these are things, here's the table. I tell you at the end, I'm going to find out from you the other acids that are, I said there are 6 strong acids, about 8 strong bases. So take a look at the table. How many did you got 3 before? What are the 3 we got? So can somebody give me the 6 strong acid now? What are the 6 strong acids?
Hydrochloric acid, nitric acid, sulfuric acid, perchloric acid. No?
Yeah, they have. So
okay.
That's 4. I need 2 more.
Perchloric acid.
I need two. What did he have before? He had 3 there before, right? So he got 4 there. What are the other 2? Can somebody give me the other 2?
Chloric acid.
What is it now?
I think I heard somebody say chloric acid. Was that one another one?
Chloric acid, yeah, is there. It's listed.
Hydrobromic
right there.
acid.
Well, that's part of the exam question.
Is it barium hydroxide?
What is it?
I can't pronounce. Barium?
What's the formula?
Barium hydric acid?
What's
There
the
you go, that one.
Barium hydric acid, yeah.
What's the formula? Give me the formula, then maybe I'll tell you something.
BA parentheses OH parentheses subscript 2.
No.
Is it acetic acid?
No.
Is it hydrobromic acid? HBr?
Hydrobromic. Yeah, HBr. Very good. HBr. One more. HI. Very good. So those are the, when we say, it's good to memorize those 6 strong acids because we have millions of acids out there. So once you know the 6 strong acids, any acid that is not on the list of the strong acid is a weak acid. That's the easy way to know what's weak and what's strong. The easiest to know the strong one, that if it's not on the list of the strong acid, it's a weak acid. You got that now, everybody? So you can't, you have to worry about all the millions of acids out there that are weak. You know, there are too many acids out there, but you just need to know which one will dissociate 100%. All right? Now look at the bases. Look at the bases. Look at the column 1. They are finding column 1 and column 2. So everybody should look up all of the strong bases. Look them up. Did everybody copy HI and HBr? If you didn't, you need to. So HCl, HNO3, H2SO4, HClO4, HI, and HBr. Strong acid. Now let's go to the strong bases.
You're missing rubidium hydroxide for the base, strong base.
Barium, you got barium, is it? Rubidium,
Yeah, rubidium and cesium hydroxide.
Yeah, and what else? How many got now?
Well, you have 6 strong bases on that chart.
You're right.
So you have sodium hydroxide, potassium hydroxide, lithium hydroxide. calcium hydroxide, strontium hydroxide, and barium hydroxide
Right.
with rubidium hydroxide and cesium hydroxide.
Okay. Okay. Do you see that now? Okay. So it's good to know these things. Anything else that are not on these lists, you know is weak. All right. Concept of ionization allows us to do what? Portray ionic solutions more accurately by showing strong electrolytes in their ionized form. All right. So the red is strong acid and bases and soluble ionic compound. You got, so remember we did net ionic equation. You remember that? Total ionic first the non-ionic equation, the ionic equation, the net ionic equation. Three of them you're supposed to write. We did that in the lab. Okay, so you see that there? Everybody see that? Okay, then anything that is in solution is called a spectral ions or net ionic equation. So it's very, very important. These things, so you need to know them. Yeah, for the examination. All right. Now, guidelines for writing. I love guidelines. Complete and balance the non-ionic chemical equation. Convert the non-ionic equation into the total ionic equation. Write strong electrolytes in ionic form. Write water and dissolve gases in the non-ionic form. Cancel spectral ions to obtain a net. So that's the guideline you need to do that. If all species are eliminated, there is no reaction. That's right. We did that before. All right. If all species are eliminated, there is no reaction. Check each ion atom on both sides. Reactant and product side, check those. So we have pH is a measure of what? Acidity of solution. A neutral solution have pH of 7. All right, so these are things we talked about earlier. All right. Acid-base reaction, what to expect, things we talk about. pH is equal to that. Hydrogen ion equal to that. KW. All right, so that's it. Congratulations. We're done with all lecture, no more lecture. No more, any questions so far? If not, let me see, what's your schedule for? Let's see. I know you'll be busy tomorrow.
What was that?
I see you'll be busy tomorrow and the 13th. So let me see you on the 18th. Everybody?
You want to see us in the video again on the 18th?
Yeah.
Okay, so not tomorrow or the next 4 days, right?
Yeah, you'll be testing starting tomorrow.
Can you say that again?
I see you'll be testing starting tomorrow.
Okay. Okay, perfect.
Tomorrow and the next tomorrow. So on the 18th, we can meet.
At what time?
Same time, class time.
Okay, 11. Perfect.
Right, okay?
Professor?
Yeah?
I logged in super late until like 11:40-ish, so I missed the whole attendance.
What's your name?
Jennifer Cervantes in group 7.
Group 7. Okay.
And Carter from group 1, I logged in late too.
Carter?
So there's class on the 18th?
Yeah, we're going to be discussing the all your stuff. Grade
Okay.
wise.
Okay.
This is Anna Bernal from Group 3. I logged in late as well.
Anna Bernal. Okay. Anybody else?
And Ezra Whitlock from Group 2.
Ezra. Okay. All right. Anybody else?
Jose Serrato from Group 7.
Group 7. Jose. Okay. Who else? Anybody else?
And
Professor-
Stephanie Mendez too from Group 4. She's having issues with her audio too.
Where is she?
Stephanie Mendez from Group 4.
Is she there now?
Yeah, she's here on the chat, but she's having issues with her audio.
Well, I need to hear from her. Okay.
Professor, I have a question.
Uh-huh.
When does the test close?
Look at schedule.
It's on the syllabus?
Yeah, it's on the silver, yeah.
It doesn't give the hours, it just says when it opens and closes. So when exactly tomorrow does it open?
Open hold on for a second, okay?
Okay.
Okay, I was looking at the syllabus. The syllabus says, if you have a syllabus with you, it says midnight, opens up midnight tomorrow.
So midnight tomorrow.
Yeah, and it closes at midnight the following day.
So we technically only have Thursday to do it.
Right.
Okay.
Or do you need midnight tonight so it opens like at 12:01 a.m.?
Or not tonight, tomorrow.
Tomorrow. Okay.
Yeah.
Okay, so wait, how many days do we have to take the test?
Just Thursday.
Thursday, yeah.
Okay, and then also if you have SPS or anything for that, do they have to let you know that we get the extra time again?
Yeah, but I think that's enough time for SPS and everybody. We got just 24 hours.
To take the whole test. So it's not like an hour and a half is what I'm saying.
Yeah. Okay.
Okay.
All right. If you have any question, let me know.
Dr. Toki,
Mm-hmm.
are we required to sign in on the 18th? Because on our syllabus, it says the last day is the 16th.
I'll give you a sign-in credit when you come.
Okay.
Yeah. I'll take roll. I'll take roll on the 18th when you come.
Do you know how long it'll be for that meeting for the 18th?
No, once you go through the grades and all that, then that's it.
Okay.
Yeah.
Okay, so when is the last day of the chemistry course in general?
They said the 16th.
Yes, so, and we're meeting on the 18th?
16th is a Sunday, I think Sunday.
Right, but I'm saying, so we're meeting on the 18th, so after.
Right, after, yeah. If you can't meet it, that's okay.
No, I will. I was just asking.
Yeah. Okay. So what I want you to do is to add up your midterm and final when you're coming in, and send that to me. Okay. I will have it. I just want to double check.
So we have to send you the grades together, in a message just to you, like like an individual one, or do we have
individual?
Okay.
Yeah.
Dr. Toki,
Mm-hmm.
another question. The homework is due tomorrow, 12 tomorrow by midnight, correct?
Yeah.
Okay, thank you.
Okay. All right, so that's it. I'll see you on the 18th.
Okay.
Have a wonderful weekend.
You too now. Okay. Uh-huh. Yeah. The concepts for running an experiment. Oh, what happened when radioactivity, take place? Yeah. Those that would change, to different elements. Yeah. Okay. All right.
Professor, sorry, this is Cynthia. I just had a question. Were you going to email me back my midterm information? Because I haven't heard from you.
Oh, okay.
Yeah, thank you.
All right. Send me a link. Send me something. Flag me now, okay?
Okay, I'll email you right now.
Okay.
Okay.
Professor?
Mm-hmm.
So we find the final exam in Canvas on assignments where we did with the midterm, correct?
Exactly. Yeah, same way.
Okay, just making sure. Thank you.
So you got an assignment, right?
Yeah, under assignments, that's where the midterm was at.
Right. Okay. All right.
Sorry, Professor. How many questions is the final?
I don't know. I gave that so long time ago. I don't know now. But I don't know, maybe it close, in a range of 20 to something,
Okay, thank you.
All right.
Did you say? Hello?
I'm not sure for sure what it is,
No, I know, but did
I know it's more than the midterm, that's for sure.
okay.
Okay? Let's look at it that way. It's more than the midterm.
Oh, I know that. Yeah.
All right. So you take care.
You as well. Thank you so much.
Okay.